The second technique we want to talk about is filtering or inference. This allows you to detect failures early and prune large parts of the search space early on. So the first type of filtering is something called node consistency, and you apply this before you perform any type of search. So typical CSP solvers, like we mentioned, operate on binary constraints. So as we mentioned, you can convert n-ary constraints in a CSP to binary constraints by introducing auxiliary variables. So far we're just saying that you're working on binary CSPs. Well, what about unary constraints? And the unary constraints are the one that look like this. X should be, for example, less than 3, or X should be equal to 1, and things like this, right? These are constraints that involve restrictions on a single variable. Well, unary constraints can be enforced by restricting the domain of a variable. So we can enforce this constraint or this restriction before running backtracking and remove that unary constraint. So for example, if you had a constraint that says X is less than 3, and you know, for example, that the domain of X1 from the problem is 1, 2, 3, 4, and 5, right? And one of your constraints says that X should be less than 3. Well, very simply, we can remove this constraint from our CSP just by making sure that we, fix the domain of X to just be 1 and 2, right? And remove everything that is, above 3, above or equal to 3. So this current domain here, we fix it, and then we can run backtracking search with the unary constraints removed. So a single variable is said to be node consistent if all the values in the variable's domain satisfies the variable's unary constraint. So like we mentioned, if you had a unary constraint that looks like this, then all you need to do is enforce this constraint on the domain, and then you can remove the unary constraint. This way, X is now node consistent. Right? So given a CSP with unary and binary constraints, we can enforce node consistency by checking the unary constraint and reducing the domains appropriately. The CSP becomes just a binary CSP, meaning it just contains binary constraints, and we can run backtracking search. So you want to apply node consistency before searching. Now we come to something called forward checking, which is our first inference to detect early failures. And you apply this during the search. So when a variable is assigned a value, there is an opportunity to filter or infer new reductions on the domains of unassigned variables. This allows you to detect early failures and potentially, backtrack earlier than what you are going to expect. So this is how filtering using forward checking does. It's a very simple process. In each search node, we're going to keep track of the remaining legal values for unassigned variables. In other words, we're going to keep track of the domains in the current search node. This can be done by maintaining a domain dictionary. So inside our search node, we will have this maintained. It's a dictionary that contains the current domains. The current domains is a dictionary where the keys are the variable names, and the values are the list or the domain list of values for that variable. Okay. And after a variable X is assigned the value X, we can check each unassigned neighbor of X and delete from that neighbor variable's domain any value that is inconsistent with the value of X. So if you have a variable X and you have neighbors of X, let's say A and B, they're both, let's say, unassigned neighbors. And imagine you have this dictionary in your current setup. Let me just write this again, A and B. Right? You have the dictionary that contains, this is the variable X, this is the domain of X here, it's a list. This is the variable A, this is the domain of A, this is the variable B, and this is the domain of B, right? And let's say you selected X and you want to assign X the value, some value, let's say small x. What you do with forward check-in is I need to check every unassigned neighbor of X, which is going to be A and B. And I said, because I assigned X, the value X, small x, I need to check the domains of A and the domains of B. What needs to be removed from the domains of A to make this assignment consistent? In other words, there could be some values here in the domain of A that is inconsistent with what we assigned for X. And so we're going to remove those inconsistent values from the domain of A. And similarly, we do this for the domain of B. Okay. And what this will do is that it will, if it reduces the domains, if at some point you have an unassigned variable that has no legal values remaining, meaning that the current domain of that unassigned variable becomes empty, that means that you've reached this is a dead end, and so you can backtrack. Meaning, this allows you to detect some failures early on, right? Because you're checking your neighbors in the current search node rather than waiting to find the inconsistency later on in the search path. So we talked a lot. Let me show you an example of this. So I'm at the root node here. Inside my search node, this is my current domain. You can see it here. All the variables have the full domain. And let's say I selected a variable for assignment and I went down and I assigned it a value. So I assigned WA the value red. Now at this search node, this is the current domain. You can see it here, right? So the domain of WA just became the value red. And because I'm using forward checking, when I assign WA the value red, I check its neighbors, right? Because I checked its neighbors, I'm going to remove the domain, the values that are inconsistent with what I assigned for red. So this is why NT now has, the red value removed and also SA. So far, there's no issues because none of the domains of my variables became empty. And so I can continue down this path. Now, again, we did filtering. This is called filtering. Now the goal is, or the next step is to select the variable from the unassigned to assign a value and go down the search path. So let's continue. Now this is the current domains in this search node. We assigned, let's say, Q the value green, and the same situation. I'm going to assign green to Q, and I need to check its neighbors, right? So its neighbors are going to be NT, remove the inconsistent values. It's going to be NSW, and it's going to be SA. So far, no inconsistencies have been found. There's no empty domains. We can continue. Now, at this search node, this is the current domains. You can see that when I assigned V the value blue, I check its neighbors, and I have an empty assignment for or an empty domain for SA. That means that going down this path is not going to get me a valid assignment. So I can backtrack and go back. When I backtrack, I'm at this level here. And so the domains at this search node is going to be this one here. Okay. And so what I want to emphasize is every single search node maintains a unique set of domains at that search node. Right? But this is how forward checking works. If any of the domains become empty at a search node, there's no point in continuing, and so I can backtrack. This is just showing, illustration of, I guess, a visual illustration of backtracking with a forward checking. So let's say I assign the value T, right? What happens to the domains using forward checking? T has no neighbors, so no forward checking is done. Then let's say the next path or the next search node assigned something to NT. I assigned it red. Now forward checking is going to be applied. You can see the neighbors. Now keep moving on. Assign forward checking. Moving on. Assign forward checking. Moving on. Assign forward checking. Inconsistency. Now backtrack. Assign another value for SA. This is the other path or the other values left for SA. Forward checking, keep moving, forward checking, inconsistency, and backtrack and keep, going on. And I hope the idea is clear. We do forward checking within the search nodes. This is FC plus MRV. I'm going to just move on through it real quick. You can see that, with FC, it detects some early failures, but with FC plus MRV, it's going to be a little bit faster. Right, it found the solution. So it seems that MRV is a good heuristic. So forward checking plus MRV seems to be a good heuristic for graph coloring. You can use degree as well. Right, and yeah. Okay, a stronger notion of checking for failures early on. That's even more powerful than forward checking. Forward checking, when you have a node and you assign it a value, you check only its immediate unassigned neighbors. That's it, right? There's actually a stronger notion called arc consistency that actually checks the unassigned neighbors. If the domains of unassigned neighbors are modified, then it also checks their neighbors and so on, right? It propagates checks across your CSP variables. And this can allow you to really check for future failures that are at lower depths early on for not much cost. So a stronger notion is something called arc consistency. It enforces binary constraints. So formally, an arc, which is a directed arc, x goes to y. So if you have a variable x and a variable y, you say that the arc of x goes to y is said to be consistent if and only if for every value of x in the current domain of x, there is some, and the keyword here is some, value of y in the current domain of y, such that the constraint between x and y is consistent or not violated. Right? So this is I would say, an involved definition. Let's look at an example. A CSP is said to be arc consistent if every variable is arc consistent with every other variable in which there's an arc between them. So let me show you a very simple CSP. Consider a simple CSP. It only has two variables, x and y, right? So this is x. It has a binary constraint with y. This is your CSP. The domain of both variables is 1 to 9 integers, and I'm showing the domain here. These are the domains for x. These are the domains for y. The constraint is that y should be equal to x squared, or in other words, if x is 1, then y should be 1. If x is 2, then y should be 4. If x is 3, then y should be 9. Right? So you can see I've added links between the values, right? If I assign x1, then a valid assignment for y should be 1. If I assign x2, then a valid assignment for y should be 4. To make x goes to y consistent, right? Then we need to make the domain of x 1, 2, and 3. That's it. That means we need to remove from the domain of x these values. Why is this the case? Right? Well, look at what this definition says, is that an x goes to y is consistent if and only if for every value of x in the current domain of x, there is some value of y in the current domain of y such that the constraint between x and y is consistent. So if we look at 1, there is some value to assign to y that makes the constraint between x and y consistent. So I don't need to remove 1. What about the value 2 for x? The value 2 for x, there is some value, so no need to remove 2. What about 3? 3, there is some value, so no need to remove 3. Okay, what about when we assign x equals 4? When we assign x equals 4, there is no value in the domain of y that satisfies this constraint here. And so x goes to y is not arc consistent with this current domain. I need to remove 4. And I need to remove 5 as well, and 6, and 7, and 8, and 9. And this is what it means to make the arc from x goes to y consistent. It means that we need to modify the domain of x to satisfy this definition. So if we modify the domain of x to be just 1, 2, 3, now this arc x goes to y is arc consistent. Okay, what about y goes to x? Y goes to x, again, is not consistent with this current domain. The main reason is because you can see 2, 5, 3, 6, 7, and 8 do not have some value in x that satisfies the constraint. So we need to remove, 2, 3, 5, 6, 7, and 8, right? So I hope the idea is clear. When you have an arc of, some variable goes to another variable, the way you would check or enforce arc consistency is there needs to be a modification of the source variable, which is a. And the way you would check it is a loop. You check every value of a. Is there some value in b that satisfies the constraint between a and b? If for a particular value of a, there is no value of b that satisfies the constraint, then you would remove that value from the domain of a. And so after enforcing arc consistency between a goes to b, the modification of the domain of A would be a reduction, or it will just stay the same. So it's either stays the same or a reduction of the domain. So with this updated domains, the CSP is fully arc consistent. So a CSP is arc consistent if all your arcs or every constraint is arc consistent. And I want to emphasize that if you have a binary constraint between A and B, you need to enforce arc consistency in both direction. From X goes to Y and Y goes to X. So given a CSP, we can enforce arc consistency on all the arcs to reduce the domains. Then we can run backtracking search. So you can run arc consistency before doing a search, such as we did here. This is an example of full domains. Before we even run backtracking search, we can enforce arc consistency, and the domains of both variables X and Y went from this domain to a reduced domain. And so this can reduce the amount of search that you do because your values or the domains are reduced. So this is applying arc consistency before the search. This is the code for arc consistency called AC3 algorithm. It is kind of, I would say, it looks intimidating, but it's easy to understand what's going on. So initially, you are given a CSP, right? And we would like to run arc consistency on the CSP. So imagine you had a CSP and there's constraints between variables in that CSP. When we run AC3, we're just checking arcs in both directions. And we are going to reduce the domain of the variables. And so that's what it means to run this AC3 algorithm. So let's see what happens in the beginning. In the beginning, you'll have a queue. The queue contains the set of arcs in your CSP. So initially, the queue must contain arcs in all directions. So if you have a constraint between two variables, xi and xj in your CSP, right, you need to add in your queue both directions. And we're going to just use a tuple to denote it. So xj just denotes the direction from x goes to xj, and xji denotes the direction from xj goes to xi, right? So your queue initially contains all arcs in your CSP, which is meaning all edges in both directions. Okay. And the way we're going to implement the queue is we're going to implement it as a set, right? Meaning if you understand sets mathematically, mathematically is that, if you have a set that contains, an arc A goes to B, let's say, and then you add the same arc A goes to B, it's not going to be duplicated. That's the reason we want to use a set, and you'll see here in the code why we want to implement it as a set. So while your queue is not empty, meaning you have more arcs to process, what we're going to do is pop an arc from our set, and now we want to check and enforce arc consistency on the arc, mainly the arc xi goes to xj. If you look at this code, you can inspect it on your own time, but it's a very simple code. It just checks that for every value x in the domain of xi, so it checks every value x in the domain of xi, we'll just denote it as di. If there is no value in the domain of xj that allows xy to satisfy the constraints between xi and xj, then what I need to do is I need to remove x from the domain of xi. And that is what this does. This code just enforces arc consistency between the arc xi goes to xj. And if there was any deletion, meaning there was a revision that happens, reduction that happens to the domain of di, then I want to return true from the call. So this checks the following. If I'm checking this arc and there was actually a reduction in the domain, so this evaluates to true. There's a reduction in the domain of xi. Then what I need to do is check the following. If the size of a domain of the variable xi goes to 0, then that means there is no solution for this CSP. So imagine you run this AC3 algorithm, and as it's checking the arcs, one of the domains of one of the xi's goes to 0. In that case, that means there's no solution. And so you can, you don't need to even run backtracking. This problem has no solution. Another thing is that if a domain, now this is important, this is where AC3 or arc consistency becomes powerful. If an arc xi goes to xj, if you did the revision and the domain of xi was modified, this function will return true. If a domain of the variable xi has been modified, then this, you need to do it. You need to check for each xk that is in the neighbors of xi, that means if I had an xi and I'm checking the arc from xi goes to xj, and I found that the domain of xi was modified, then I will need to add the arcs of the other neighbors of xi. So I will need to add the arcs from, if this is one neighbor from x1 goes to xi, and I needed to add that arc to the queue, and the neighbor x2 goes to xi. And this needs to be done for all the other neighbors of the variable whose domain was modified. The reason you want to do this is because the modification of the domain of xi may have made the arc from x2 to xi and x1 to xi no longer arc consistent. Remember, x1 here has a domain and x2 here has a domain. Because you have modified the domain of xi, it could be that this domain is no longer arc consistent. And so you need to re-add those arcs to the queue and recheck their consistency. And so this is why, and this again, if you recheck the arc from x2 to xi, this could also be modified. And if you modify the domain, then you need to check the neighbors of x2 and add their arcs again to the queue. And you keep doing this, you can see that arc consistency is much stronger. It propagates constraint checking to the remainder of the neighbors and the graph in general, right? So this code enforces arc consistency. It starts initially with all the arcs in the CSP and propagates arcs and checking the consistency. Once the code completes, it completes when you have no longer arcs in your queue, and that means that your CSP is now fully arc consistent. And you can, I'm going to give you something where, something that eases your mind, that this algorithm will terminate. The simple reason is because the following. With n variables and d max domain size, at most there are on square arcs in your CSP. معناتها if you have a CSP with n variables, right, it means there are n vertices in your graph. How many edges can you have for a binary CSP? If you have n vertices, then the total amount of edges that you can have is on square. It cannot exceed on square, right? So the total number of arcs in my queue is going to be on square. Each arc can be inserted into the queue at most d times. معناتها for each of these n square arcs, you can only re-add them to the queue d times. Why is this the case? Because anytime you do a revision to xi, you are going to reduce its domain by at least one value. And there's only d values only. So you can only reduce the domain d times. Each time you reduce a domain, you will add a neighbor arc back into the queue. So each arc can only be added at most d times. Okay, and so checking and lastly, checking the consistency of an arc is going to cost you OD square. So in total, the number of time, the cost of this code here, this revised function here, is OD square. The number of times this loop executes is going to be on square d. And so we have a loop that is going to run for on square d, and inside this loop we have something that runs for OD square. So in total, the runtime for this algorithm is on squared d cubed in the worst case. This is for this particular implementation. There's another advanced implementation called AC4 that takes on squared d square. It uses some optimization for the memory. We won't really discuss it, but it's good to be aware for your professional life. So that is the arc consistency algorithm, AC3. And we said that you can run this before you do searching so that you can hopefully apply arc consistency on the domain of the CSP. This results in smaller domains, hopefully, and that will reduce the amount of search you do if you decide to apply backtracking on this reduced domain. Another thing you can do that's very powerful is you can run the AC3 algorithm during the search. What we saw with forward checking is that it propagates just to the current immediate neighbors, right? With arc consistency or AC3, you can propagate to the current neighbors and also from those neighbors propagate to another, let's say, neighborhood of neighbors. So it's more powerful. So If we check this scenario in my search, I'm at this node, I move down, I'm at this node, I move down, I'm at this node, and I move down one more. At this level in the search tree, you can see that arc consistency doesn't detect for this domain any problems, right? However, we already, if we applied AC3 at this level, it can see that, hey, I have two neighbors, SA and NT, right? You can see that SA and NT are neighbors. Because they only have one domain or one value left in the domain, this this assignment here or this remainder path is no longer valid. Forward checking will not be able to detect this. However, if you applied AC3 at this level with this current domains, it will check that the domains will go to 0 for SA or NT, whichever we're going to see it right now. And so you could have detected the failure early and backtracked early. So after assigning Q equals green, NT and SA cannot both be blue. Detecting failure early would be better. We can run AC3 during backtracking. So let's see how this is done. I'm going to show you how AC3 can be run during backtracking and show you how we were able to detect it. Now I want to emphasize that what I'm showing you here is done within the search node. So if you remember, forward checking, after a variable is assigned a value, we applied forward checking on the neighbor's domains, right? The same thing with AC3. When a variable is assigned a value, then we reduce the domain of that assigned variable, right, to just the value that it was assigned. Then we can apply AC3 on the current domains. And then after applying AC3, the cost of AC3 is going to be O(n) squared d cube, right? In the worst case, so every search node, you can run AC3 with a cost of O(n) squared d cube, so that hopefully you can detect failures early on. So after assigning a value to a variable X, we can run AC3. Now, this is important. When you run AC3 within a search node, your queue is not going to be all arcs in the CSP. Because we assigned X a value, we just need to look at the arcs that are neighbors of X. So we look at Y's, which are all neighbors of X, and we add the arcs of Y goes to X. So if I had a variable X and it has neighbors A and a neighbor B, let's say, and I assigned a value to X, then when I want to run AC3, I just need to, I don't need to put all the arcs in the CSP, right? I may have other arcs, right, in my CSP. I just need to start AC3 with a queue that contains just, the arc A goes to X, right? And the arc B goes to X. That's it, right? The neighbors of X, right? And when AC3 runs, there is potential that I modify the domain of B. And so if B had a neighbor, that arc will also be added and so on, like propagating the arcs. And you should only add the unassigned neighbors, right? There's no point in adding the assigned neighbors. So at this point in the search, I have assigned WA a value. That means if I'm going to want to run arc consistency, I want to add the neighbors, the unassigned neighbors of WA. The unassigned neighbors would be the arc NT goes to WA and the arc SA goes to a WA. So we can run AC3 with the arc NT goes to WA and SA goes to a WA. So here I'm going to run AC3. So when we run AC3, we need to pop an arc, right? Let's say we pop an arc. This is my current queue. Let's say we pop NT goes to WA. When I check NT goes to WA, I need to check every single value here against, is there some value that WA can take that makes this variable consistent. So if I assign NT red, there is no value in the domain of WA that makes it consistent. So I have to remove, red from the domain. What about green? Green, there is. I can assign WA red. What about blue? There is. I can assign WA red. Now, this is an important thing. When we're applying arc consistency, remember, I checked the arc NT goes to WA. The domain of NT has been modified. That means I need to add the neighbors, and this is where the propagation comes in. I need to add the unassigned neighbors of NT arcs. So since the domain of NT was reduced, Q goes to NT and SA goes to NT needs to be added to the queue. So my current queue contains the following, and these are my current domains. Let's say we pop SA goes to WA, right? So I'm checking this arc, SA goes to WA. I need to remove the value red. the domain of all the other values, green and blue are fine. Because the domain of SA has been modified, I need to re-add their unassigned arcs, arc neighborhoods. So since the domain of SA was reduced, then that means I need to assign, I need to add Q goes to SA, and I need to add NT goes to SA, NSW goes to SA, and V goes to SA. Right? You can see them all are added here. Again, pop an arc. AC3 will pop the remaining arcs in the queue and check them. So you can do this at home, but if you pop all of these arcs, right, this is the current domain so far, you will see that the domains will not be modified. Everything else looks fine. So then the queue becomes empty and AC3 stops. So I want to say that during this node, we applied AC3 fully for this assignment, and we ended up with this current domain here, right? NT will have these two values, and SA will have these two values. And so now we can select a variable from this domain and assign it a value and move down the search path. So let's say we assign Q equals green next. When we assign Q equals green, this becomes green here. Then the assignment of Q equals green in my search node here. I have the search node here. Q is assigned green. This is my current domains down here. I then want to apply AC3. Remember, when you apply AC3, we just need to add the neighbors of the assigned variables. So we'll add NT goes to Q, SA goes to Q, and NSW goes to Q. Right? NT, SA, and NSW goes to Q. We can pop these arcs and check them. This will remove green from the domain of NT, SA, and NSW, meaning, if you check the arcs that we just talked about, it'll remove these domains. So it'll remove NSW, it'll remove green from SA, and it'll remove green from NT. And that's it. There's no more remainder. You can re-add the arcs, right? After adjusting domains, you will re-add the arcs of unassigned neighbors. And we did not add Q goes to NT since Q was just assigned, right? You are just going to add the unassigned neighbors. That's it. This is my current situation with the Q. Let's say we popped V goes to NSW. We check that we check this. There's no issues. If you assign red, you can assign this blue. If you assign green, you can assign this blue. If you assign blue, you can assign this red. So there's no issues with this arc. This is my current Q. Let's say we pop SA goes to NSW. Again, no domain changes happen here. This is my current Q. Let's say we pop NSW goes to SA. If we check NSW goes to SA, we need to remove blue from the domain of NSW, and then we need to re-add unassigned neighbor arcs. And then finally, let's say we popped from the queue SA goes to NT. Okay, when we pop SA goes to NT, we can see that the domain of SA was reduced and it became 0. We can stop AC3 and backtrack. When the domain of a variable for when you apply AC3 during the search goes to 0, this search path down at this point in the tree is, there's no point in continuing. So you can stop the search and backtrack to the parent node. One interesting thing as well, you notice that when we assigned the value green to Q, and we had this arc in the tree in our queue, the order in which we pop the arcs, because we're using a set, there's no particular order in which we pop the arc, right? It's kind of unordered popping because we're using a set implementation. However, what I want to say is that the order in which you check arcs can influence how fast or how much work you do during AC3. And what I mean by this is there is an arc inside your queue from SA that points to NT. If you were to pop this arc as the first arc from your set, then you would have checked that this is, an invalid assignment, and you would have stopped without needing to check the other arcs. Of course, this is hard to determine how to order the arcs in practice, but I just wanted to emphasize this note that we're implementing this as a set, and so the order in which arcs are popped is kind of unordered. So arc consistency can detect failures like this earlier than forward checking. However, this requires more computation. We mentioned that with forward checking, it is a linear cost because you're just checking the immediate neighbors of the assigned variable. Whereas if you use arc consistency, yes, we're checking the immediate neighbors of Q, but then if the domains of the neighbors are modified, then we'll need to check their neighbors. And if those domains are modified, then they check those neighbors and so on, right? So it requires more computation. In the worst case, we're just going to write an upper bound that's easy for us. It's O(n) squared d cubed, which is the cost of checking the full CSP. The check is done in each search node. So it's strictly more powerful than forward checking. And you might wonder, okay, every time I'm in a search tree node, right? If I apply AC3, right, and I'm going to pay some computation cost, is this even worth it? Well, don't forget that your search tree in total is going to be of OD to the power of n. This is exponential cost. And so if I can apply, a sub-exponential cost like O(n) squared d cubed at each, search tree node, and that hopefully can reduce huge amounts of this d to the power of n and makes me go down the path to a solution faster, this can be worth it. Okay. And so we can see in practice that AC3 is very, very powerful for a large number of problems. You can solve many, many huge CSP problems with many variables in a few seconds if you apply AC3. So this is an example of graph coloring with AC3. This is all just just from assigning NT, our consistency is propagating constraints, right? And we can already see that there's no constraint needed to be propagated here. We can already see that maybe we can check if this is a valid assignment, right? Actually, we can stop here. A solution has been found, right? I just need to assign the remainder variables, the domains that's left. All the domains went to 1, and so I can check if this is a valid solution, and if it's not, I can backtrack from this level. There are limits to arc consistency. So after applying arc consistency, you can have one solution left, like in this situation. You can have multiple solutions left, like in this situation. And you can have no solutions left and not be able to detect it. So in this situation, because there is all these three variables are kind of intertwined together in binary constraints, if we have an inequality constraint, like this was graph coloring, there is no solution in this situation. But AC3 will not be able to detect this. And if you wanted to detect this, you need to apply stronger notion of consistency. Can we enforce a stronger notion of consistency? Yes. There are concepts of increasing degrees of consistency. We actually won't go into the details of this. You can find more references in the book and online if you are interested. For our purpose of this course, we are just interested in one consistency, which is the unary constraints enforcement, which is the node consistency. So if you have a CSP with unary constraints, you are going to enforce node consistency by enforcing the unary constraints on the domain. Two consistency is what we just talked about, which is arc consistency. For each pair of nodes, any consistent assignment to one can be extended to the other. And there's something called case consistency. So there's 3 consistency, 4 consistency, all the way up to n consistency, where n is the number of variables. For any k nodes, any consistent assignment to k-1 nodes can be extended to the kth node. So in arc consistency, we're just checking, an arc of assignment one variable versus another. In k consistency, you check an assignment of k-1 variables versus one more variable, right? So this is stronger notion. And for example, 3 consistency can allow you to detect failure in this scenario. However, you are going to pay more computation cost, right? And so this is just for your reference. We won't really go into more details than this. For our case, we're just interested in one consistency and arc consistency. And so this is the pseudocode for the entire backtracking. One thing we add is that at this, so you can read this at home, this text here and this text here as well. One important thing is that after a variable is assigned a value, remember this is your search node, after a variable is assigned a value, what we can do is we can do filtering at this stage, right? Remember we looked at forward checking, we can apply forward checking at this stage. And we can also apply AC3 at this stage with a suitable queue. And so inshallah in class, we'll look at, implementing this and, writing the code for AC3 and running it. And with that, we finished, I would say, the techniques that you can apply with the backtracking search algorithm. So you can do variable ordering, you can do value ordering, you can do forward checking, and you can do arc consistency or AC3 checking. And hopefully this will reduce the search work. One last thing I want to talk about, which is something called exploiting the problem structure. And this will allow you to find ways to reduce the search heavily in your problem. So one idea to reduce the search, the amount of search work that you can do is break down your CSP into independent subproblems. So sometimes the CSP can be decomposed into independent, smaller CSP problems. And the way you can detect this is by visual or inspecting the constraint graph. So if we look at the constraint graph here, we can see that there are two connected components. This is one, this is one graph. And here's another connected component. This is another graph. Okay. And when you inspect these two components, you notice that they are independent CSP problems. I can just solve or run backtracking on this connected component, find the solution for the variables involved in it, and then run backtracking on the other connected component. And if you had, a much more complex problem, you can, inspect the constraint graph and then find many opportunities for independent CSPs, right? So the idea is that maybe your CSP can be broken down into smaller CSPs or connected components. You will want to find the solution of each subgraph independently. Suppose a graph of n variables can be decomposed into n over c subproblems of c variables each. How much reduction can I get if I run for each of those, n over c subproblems? I run backtracking on that. Worst case cost of backtracking is going to be ON divided by C times D to the power of C. Where is this coming from? Well, I have N over C CSPs. That's how many subproblems there are. Each subproblem is going to cost me, in the worst case, I run backtracking on it, D to the power of C. Without decomposition, it's going to cost me, sorry, this is a typo. It should be D to the power of N. It's going to be exponential in N. So this should be D to the power of N. Just to give you some numbers, if N equals 80, I have 80 variables. These variables can take on two values. And let's say that I have 4 subproblems. I can decompose the problem where each subproblem will have 20 variables. If I try to run the CSP or backtracking search on the 80 variables, it'll cost me, in the worst case, 2 to the power of 80, which is about 4 billion years if I had a processing power of 1 million search nodes per second. Versus if I try to do it the subproblem way, so I run backtracking on the 20 variables for all the 4 problems, it'll be 4 times 2 to the power of 20. This is going to cost me 0.4 seconds if I have 1 million nodes per second processing power. So you can see that, breaking your problem into independent CSPs and running backtracking on each of those independent problems can really save you a lot of time. The second idea is something called tree structured CSPs. If the constraint graph is tree structured, meaning it contains no cycles, then the CSP can be solved in OND squared time, right? This is very attractive. That means I went down from D to the power of N exponential down to just OND squared, right? And what do we mean by tree structured? It means it looks something like this. There is no cycles in your graph. And checking whether or not a graph contains cycles, it can be done in ONV plus E, right? So it's going to be linear in the number of edges and vertices, right? It's just the size of your graph, right? And so checking if a graph is tree structured is not going to be costly. But if you had a tree structure, so you check if your graph is tree structured, and if you know it is tree structured, then you can apply a very unique algorithm that gives you a lot of savings costs to solve this CSP. So what is this tree structured algorithm? Very simply, let's try to apply it to this CSP. And let's say this was a graph coloring problem. And what you do is as follows. And first of all, topological sort, you want to choose a root variable, and order variables so that the parents precede the children. So this is a tree-structured CSP. You want to topologically sort the vertices, right? And for a tree-structured CSP, topological sort just means you want to find an ordering of the vertices such that the parents are going to come before the children in this list. So one topological sort for this tree structure CSP is as follows: A, then B, then C, then D, then E, then F. And I want to say that, given a tree structured graph, to find the topological sort is also going to be linear in the size of the graph. This is easy to do. So this is a topological sort for this graph. All right. Next step is look at the domains that you currently have. Let's say this was the current domains of your problem. And you can apply OND square algorithm to solve this. This is how it looks like. For I equals n to 2, so start from the end of your variable ordering, right? So this will be n, and this, let's say, will be index 1, and this will be index 2, this is index 3, and so on. So start from the end of your ordering. Enforce arc consistency between the parent of the parent of xi and xi. So that means starting from the end of your ordering, and this will be f, enforce arc consistency between f and its parent. So enforce arc consistency between d and f. If this is a graph coloring problem, then we check the arc between d and f. It'll be like follows: for a value of red, is there a value for f that can be assigned? Yes. For the value of green, is there a value for f? Yes. For a value of blue, there is no value in the domain of f, so we need to remove the blue from the domain of d, right? Then move your it says from I equals n to 2. So now check for n in minus 1. Check e with its the pointer from the parent of e, which is d, to e, right? So now we check. Remember, this was removed from the domain of d. Now we check this arc. If we assign d red, e can be assigned green. If we assign d green, then e can be assigned blue. So no reductions need to happen. Now check the arc between b and d. My pointer now is here in my loop. If we assign green, this can be assigned red. If we assign blue, this can be assigned red. So no issues. Now my pointer is here. If we assign the parent, the arc from B to C. If I assign green, then there's no value for C that can be assigned, so I need to remove green from the domain of B. For blue, it's fine. Then the pointer is here. Finally, check the arc between the final parent and B, which is A goes to B. If I assign it red, it can be assigned blue. If I assign it blue, there's no value, so I need to remove it. So after checking this line, these are the domains that I currently have. Okay, the cost of this step, as we can see, it is an ON loop here. And the cost of enforcing a parent is going to be, in the worst case, OND squared. Okay. Finally, with these current domains, I'm going to loop from I equals 1 to n. I'm going to assign xi consistently with the parent of xi. So I start from here. It has no parent. I just pick whatever value is in the domain. So I'm going to pick red. Then move the pointer forward. When I select a value from the domain of B, I need to select it such that it is consistent with the parent, right? And one thing you notice about tree structure CSP, once we have a topological order, there is only one parent for each variable. So I can just assign it blue, move the parent forward. I can just assign it green, move the pointer forward. Now at this level, you can see that I can assign it green or red. Both will be okay, so I can assign it green. At this point here, if I assigned D green, then I know it says here that I need to assign E a value that is consistent with the value assigned for the parent. So when if I assign D green, then I can only assign E the value blue, and then finally I can assign F the value blue because that's fine with what you assign to its parent, right? And so you can run this in ON, and this check will cost you D square as well, right? So in total, this algorithm will cost you ON D square, right? So this is the pseudocode. You can go over it on your own time, but it's very easy to see it. The last thing I want to talk about is something called cut set conditioning. So we have an efficient algorithm for solving tree structured CSPs. How can we reduce general CSPs to tree structured? Because in most cases, your CSP will not be a tree structured graph. There will be loops in it. Well, because we have this tree structured algorithm, what we can do is that we can apply something called cut set conditioning. And the idea here is that you want to remove nodes from the constraint graph. So you have your constraint graph, it contains cycles. What you can do is remove nodes such that the resulting graph, after removing that node and its corresponding edges, will become tree structured. Right. Another technique you can use is called tree decomposition. In this case, you collapse nodes and you morph the graph. We won't be discussing this. This is you can, for those interested, you can check it out in the book. It's a little bit more technical topic, but this one is much easier to grasp. So we'll talk about it. So what does the cut set condition algorithm do? It works as follows. Given your CSP, you want to select the subset S of variables such that the CSP becomes a tree after the removal of the S nodes. So if you look at the CSP, this is not a tree structured CSP. There's cycles all over the place. However, we want to find a subset of variables such that, the minimal subset of variables such that if we remove those variables, it becomes a tree. For this graph, it's very easy to see that if we remove SA and its corresponding edges, then I will get a tree that results from it. And so I can run my tree structured or tree structure CSP algorithm to efficiently solve this underlying tree. And based off of the values that I assigned SA initially, so the idea is that the way you would apply it is, for the variables that the subset of variables that if you removed it will result in a tree, you want to assign values to that variable. So let's say I assigned the SA the value red. Once you assign SA the value red, you can enforce the domains of its neighbors, and then with those updated domains, you can run the tree structured CSP algorithm on the updated domains. If there is no solution, then backtrack and try another value for SA, let's say green, update the domains, and then apply the tree structure algorithm, and so on. For each consistent assignment of your subset of variables, you remove from the domains of unassigned variables inconsistent values, apply the tree CSP algorithm on the remaining variables, then return a solution if successful. With the cut set size of C, meaning this is the number of variables that you remove from the constraint graph, D to the power of C is how many choices you need to check for the variables that you removed. So for example, if I have a graph, a graph of n variables, and let's say I want to remove, a set of nodes, and the number of those nodes is C. The number of choices that I need to assign for those nodes that I've selected to remove is going to be D to the power of C, right? I need to, in the worst case, I might need to check all of them. And then once I assign values to those subset variables, I can remove them from my constraint graph and then run the tree CSP algorithm on the remainder. The tree CSP algorithm will cost me n minus C D squared in the worst case. So hopefully, the size C should be as small as possible, right? Because you don't want to incur too much cost here. This is fine to incur the cost here because it's not exponential. So this is just an illustration of what I mean by this assignment of the cut set variables. It looks something like this. Choose a cut set SA. We need to explore, in the worst case, all possible assignment of the cut set variables. So initially, your algorithm should go down this path, right? Assign, right, the cut set variables values, and now operate on the tree CSP here. If this is a no-go, you backtrack to this level, and then explore this part. If this is a no-go, then backtrack and then try other values for your cut set and so on, right? And this is how you apply cut set conditioning. And with this, I will stop here. Jazakumullah khair. This is everything we want to cover in terms of the CSP topic. جزاكم الله خير والسلام عليكم ورحمة الله وبركاته.